Okay. So today we continue with spontaneously broken gauge theories. Specifically, now we learn how to renormalize them in the arc-side gauge that was defined last time. And the example we're gonna use is the SU2 Higgs system, since, well, is the simplest non-abelian case and also is the closest to electroweak theory without being exactly it. And I also will not do the full renormalization theory. I'll just sketch some of the important steps. All right, so first, let's define this SU2 Higgs model. So SU2 has a SU2 gauge fields and a complex Higgs doublet. As usual, we have this ambiguity of terminology. I mean, one says Higgs doublet, but really the Higgs field is H in the transverse direction to the symmetry direction. And then there's the would-be Goldstone boson Chi-A. One important difference with respect to the unbroken gauge theories is that we will see there's one more word identity given by the fact that we've split one component of the SU2 doublet into a VEV V and the Higgs field H into going in the same direction in group space. So we have this combination V plus H that appears in the classical Lagrangian. And the gauge fixing term will depend only on V, not on V plus H. So that makes it, that means that the quantum, at the quantum level, the quantum action, effective action will be, will not have this symmetry manifest, but that's why we actually need word identities. We parameterize the complex field slightly differently than before. Let's consider the first the VEV in the upper component and instead of the lower component, and it's still a real VEV. So I would write, being a doublet, I would write phi1, phi2 up and down. But the parameterization that we choose for the real and imaginary lower and upper components are as follows. So we write phi as 1 over square root 2 psi plus I chi a sigma a, where sigma a are the Pauli matrices, times the column vector 1, 0. Explicitly writing explicitly what that means is 1 over square root 2, and then psi plus I chi 2, chi 3 in the upper component, and I chi 1 minus chi 2 in the lower component. Then you see that in the upper component, this psi, the real part of the upper component, will basically be V plus H, so the VEV plus the Higgs. And then the other three components, chi1, chi2, chi3, written together as chi A, will be the would-be constant boson. The Lagrangian is, as usual, the gauge field part minus 1/4 Fa mu nu squared, the Higgs doublet kinetic term minus d mu phi dagger d mu phi, and the potential part minus V of phi dagger phi, where V is a constant, minus mu squared phi dagger phi plus lambda phi dagger phi squared. And then from the fact that the vev of the real part of phi 1 is V over square root 2 means psi is V plus H, as we said. And the gauge covariant derivative then is written with the same sigma a's, the same Pauli matrices, now understood as the generators of SU2, specifically sigma a over 2 being the generators of SU2. So the covariant derivative is d mu phi minus I over 2 g a mu a sigma a phi. This is, of course, a particular case from the general non-abelian procedure from the last lecture. And following that, we'll write the Lagrangian that comes from this covariant derivative term as a sum of a kinetic piece, a quadratic in the fields, a piece linear in A, and a piece quadratic in A. So kinetic term is kinetic term for the Higgs and plus kinetic terms for the Goldson boson. So minus 1/2 d mu H squared minus 1/2 d mu Ka squared. The linear part in A has a mixing between A, the gauge field, and the would-be Goldson boson, the usual one. GV over 2, A mu A, d mu Ka. Then there's an interacting part, linear in A. So G over 2, A mu A, Chi d mu Ka minus Ka d mu H d mu Ka minus Ka d mu H. Then plus 1/2 G epsilon ABC, Ka A mu B, dA Chi C. And finally, there's a quadratic piece in A, which is minus G squared over A mu A squared, V plus H squared plus Chi B squared, which of course also contains the mass term for the gauge field in the term with V squared in here. So the mass is, as usual, GV over 2. Then the covariant derivative becomes the covariant derivative of phi becomes, so I wrote it like this, but then remembering this expansion becomes, so we wrote the both of them in such a way that this is now written as 1 over square root 2 covariant derivative of H plus I sigma A covariant derivative of Ka. So here, covariant derivative of H is normal derivative plus G over 2 A mu A Ka. So it's covariant derivative, but not in the normal sense. So there's the gauge field as A mu A, so it couples to Ka, not to phi, to H. And covariant derivative of Ka has this normal part, so d mu Ka plus G over 2 epsilon ABC A mu B Chi C. And then also a term where it acts on the other component, so minus G over 2 A mu A V plus H. But then in terms of this, it means that I write the scalar kinetic term as minus a half d mu H squared minus a half d mu chi A squared plus GV over 2 A mu A d mu chi A, the mixing term. To cancel the last term, as you remember from last lecture, we add the 12th gauge fixing term known as the arc psi gauge, exactly with this mixing term with opposite sign. So gauge fixing term is minus 1 over 2 psi d mu A plus 1 over 2 psi GV chi A squared, such that the cross term with the partial integration, so d mu instead of acting here is put to act on the other side, gives us cancels this term. Sorry, there's probably a wrong sign in here. I think this is minus. Well, I'm pretty sure it's minus, because otherwise doesn't work out. So there's a minus sign in the cross term, but then I partially integrate the derivative. I get a plus, so it has to be minus here. Then the quadratic term for chi squared, for chi is minus a half d mu chi squared, chi A squared, of course. Minus psi over 2 GV over 2 squared chi A squared. So that means that, as usual, we have the mass of the Wolfson boson being square root of psi times this GV over 2, which is the mass of A. So the kinetic term for the vectors then is this gauge invariant kinetic term, the usual one, minus a quarter F mu A squared, then this mass term, minus a half GV over 2 squared A mu A squared. And the ghost Lagrangian is also, as usual, the variation of the gauge fixing term, gauge fixing function GA divided with respect to the parameter alpha b in between BA and CB, which gives, considering that this is GA, the gauge fixing function, so the variation of A is covariant derivative alpha, so divide by alpha, we get d mu d covariant derivative. So the first part is BA d mu covariant derivative del mu d mu CA, and then the second part comes from the variation of sorry, here, the variation of chi A. And that corresponds to these other terms. So this is a piece corresponding to V plus H, and the piece corresponding to psi. So the piece corresponds. So this is all multiplied by this psi GV over 2. So the piece corresponding to V gives now a mass term for B and C, psi GV over 2 squared BACA, which means, as usual, that the B and C ghosts have the same mass as the would-be ghost of boson and the longitudinal part of the Yang-Mills field, making a quartet of unphysical states, all of them with mass square root psi times GV/2, which is the mass of the physical or transverse gauge field, gluon. And then this last piece is just an interaction piece between two ghosts and one scalar, either the Higgs or the would-be ghost of boson. Yeah, again, this should be minus here, I think. Now, we'll see why shortly, but at the quantum level, so at the classical level, I wrote the same psi both here and here. And the reason was that in the cross term psi in this way canceled, and then that allowed for this cross term to be of this form, so canceling the classical level, canceling this piece coming from the scalar kinetic term, this mixing, right? But we will see why shortly, but at the quantum level, the gauge fixing term is written with independent parameters. So the Feynman-like parameter in the gauge fixing term, so in general, the gauge fixing term is -1/2 times this alpha Feynman-like parameter times GA, the gauge fixing function, squared. And then inside the gauge fixing function, I have this psi parameter. So now alpha and psi are different. And yet, we will still find, even at the quantum level, that the quartet of unphysical states have the same mass. And as we said, this is so because in this way, in loops, the unphysical states cancel each other. We shouldn't have loops. I mean, because in principle, we could choose a unitary gauge without any unphysical states, and in this, and then the physical observables will come from loops of only the physical states, which means that the loops of unphysical states should cancel. And that means that they would have the same mass in principle. That's roughly the reasoning, but it's more complicated to actually prove it. Okay. Let's now look at the quantum theory and derive for the quantum effective action. We will also derive the corresponding Lie-Sanger-Stein identities. So in the Lagrangian, there's a gauge part, which is the kinetic term for A mu A. So -1/4 d mu A mu A minus d nu A mu A plus G FABC A mu B A mu C squared. Then there's the matter part. So the covariant -1/2 covariant derivative of phi squared minus the potential. And as we saw before, this was -1/2 covariant derivative of A squared minus 1/2 covariant derivative of chi A squared plus this part coming from the potential, mu squared over 2 V plus H squared plus chi A squared. This is from phi squared. Then minus lambda over 4 v plus h squared plus chi a squared, everything squared. This is from the 5/4 term. In principle, there was also a mixing term, but that canceled with the mixing term from the ghost. And then we're left with b del mu d mu ca, the usual usual kinetic term for BC ghosts, minus this psi gv over 2 times 1/2 gv plus h ca plus 1/2 g fabc chi b cc. And then, so this is from the classical plus ghost plus gauge fixing term, right? But we still need to add terms to the Lagrangian. So in the unbroken case, we know that we shown that in order to do renormalization in an easier way, we need to add extra source term to the Lagrangian corresponding to the nonlinear parts of the BRST variations. So the BRST variations that have that are linear will not have sources. So in particular, the BRST variation of B will not have a source. But for the other ones, we do. So we have, for the BRST variation of the gluon, of the full scalars, and broken into the Higgs and the would-be ghost and boson, and also for the BRST variation of Ca. So we'll have source k mu a for BRST variation of a mu a, so times this BRST variation qb a mu a over lambda, and then source k for BRST variation of h. So here we split the source for the BRST variation of the full scalar into part for the Higgs and part for the would-be ghost boson, and then k is the source for the BRST variation of h, qb h over lambda, and ka is the source for BRST variation of chi a, qb chi a over lambda, and la is a source for BRST variation of Ca, so qb Ca over lambda. And the BRST variation, remember, is just so for the classical fields is just the classical variation, where I basically remove the variation parameter and replace it with C. So I have k mu a times d mu, here will be an alpha a, but now it's Ca, and then minus k 1/2 g chi a Cb, normally be alpha a, but now it's Ca plus Ka times, so this is only for the nonlinear part, so everywhere we only keep the nonlinear part. The linear parts, we're not sourcing them. So even though I write it like this, if there's a linear part, I drop it. Then chi a times 1/2 g v plus h Ca plus g over 2 fabc chi b cc plus la 1/2 g fabc cb cc which is the nonlinear part of the variation. The variation of CA, which is nonlinear. Okay. One useful thing to do is to write the linear and quadratic mass terms in the scalars as in terms of this beta, which is minus mu squared, the mass term in the potential, plus 2 lambda v squared. So in this way, the linear quadratic terms will be minus beta vh minus beta over 2h squared plus k squared. I mean, in this way, so mu squared and lambda v squared, as usual, we normalize multiplicatively, but as a result, beta itself does not renormalize multiplicatively, because the renormalization is, as usual, understood as 1 plus correction of correction in order perturbation in order g squared. I mean, even if it's perturbation, even if it's infinity, it's morally thought as a small correction in g squared. So then the renormalization of beta is additive. So so if I write beta renormalized as minus mu squared renormalized plus lambda renormalized v squared renormalized, then classically I would have that the mass term cancels this lambda v squared. I mean, that was the point of v. The v was chosen to be mu squared over 2 lambda classically, right? So at 0th order, this canceled, and then we're left with the first and higher orders in here and in here, which therefore are renormalized additively. So you have 0 with at the classical level plus something non-zero for the 1. Right? But we'll nevertheless choose to renormalize beta like this rather than renormalize mu squared multiplicatively. Another observation is that the matter Lagrangian depends on v plus h. So I have everywhere v plus h. So the gauge fixing term, of course, doesn't. The gauge fixing term depends only on v, but not on h. So the gauge fixing term breaks the symmetry with respect to v plus h, breaks the explicit symmetry, but the gauge fixing term is part of the quantum theory. So that means that the quantum theory is written in a way that does not make explicit the symmetry with respect to v plus h, and the result of that is that there should be a word identity with respect to this symmetry v plus h. One note is that, of course, we could have written a gauge fixing term of the type with v plus h instead of v, but then it would be more complicated. So usually it's done with just v. And in this case, we'll find that alpha is different than psi, although will require that, of course, the renormalized alpha is equal to the renormalized psi, and can be chosen to be 1. So, like in the unbroken case, to write the word-like identities for the effective action, more precisely what we've called the Lagrangian identities. We write first the effective gamma hat as the effective action minus the gauge fixing term. And then, if you remember, we got 2 Lagrangian equations. One has the same form. There's a derivative from the right of d gamma, so d gamma hat with respect to the fields phi I, which are h, chi a, mu a, and ca. And there's then there's a derivative from the left, d gamma hat, d ki being the sources, meaning k, ka mu, and la for the corresponding fields here. So that was one Lagrangian identity that does not get modified since it was independent on the gauge fixing term. But then there was another identity that was dependent on the gauge fixing term, and the identity came. The identity before was d mu del with respect to ka mu minus del with respect to ba of gamma hat equal to 0, and that came from the gauge fixing term being del mu a, which couples in the quantum action with, I mean, its BRC variation couples to k mu a. So, but now we have a gauge fixing term that doesn't have only this, but also has, so besides this del mu a mu a, has also psi gv over 2, psi gv over 2 chi a, and chi a couples to ka. So correspondingly, I have here minus psi gv over 2 del with respect to ka as well. All of this acting on gamma hat. So this is the second Lagrangian identity. And then, of course, this extra term is linear in V. So when I put V equal to 0, I go back to the unbroken case. Okay, so we have then the fields a mu a, ba, ca, h, and chi a, and for sources for them k, ka, k mu a, and la. And also we have the parameters g, v, lambda, alpha, and psi. Okay, so how do we renormalize things? Well, we renormalized first, we renormalized the fields, a mu a with what is historically called square root z3, as we remember, the ghost b and c with square root z ghost, and then extra for the scalar fields, for the Higgs h with square root zh, and for the would-be ghost boson chi with square root z chi. But then once we do, once we renormalize the fields this way, then the renormalization of the the normalization of the sources is fixed in terms of this field renormalization, and the result is that the reason is that we have in the quantum action we have these terms, the source terms are source times BRC variation of field, right? So I have K mu A, Q B A mu A, K Q B H, K Q B K A, and LA Q B C A. And then this variation itself is written in a specific way. So we wrote, so here we wrote K mu A d mu CA for this variation, then K GA K B CA over 2, and so on. So let's be more precise. So K mu A, for instance, has the first term here is d mu CA. So so this means that the field, you compare this with the other term in the action, which is BA del mu CA, del mu squared CA. And you see that K mu A should renormalize as BA. So K mu A then renormalize that with Z square root Z ghost. Then let's see what is next. K. So K, as compared with BA CA, BA del squared CA. So it should renormalize as B divided by KA. So so square root Z ghost. Oh, sorry. There's a coupling as well. Sorry. It's divided by the renormalization of the coupling times K. And so it's square root Z ghost divided by square root Z KA. And then the renormalization of the coupling gives this square root Z3. And then the same way for K. I mean, that's just because, well, so K couples, K and K are sources for the scalars, and then the scalars is the same kind of renormalization for either scalar. So this has the same renormalization. And finally, LA. 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 So this would be the same. So there would be a term with d mu A mu A times this variation. So LA should renormalize the same way as the gauge field. So with square root Z3. Then the renormalization of the parameters the G is renormalized with ZG, and then I also have this also gains a dimension which has to be compensated by this dimension transmutation scale mu to the power of 4 minus d over 2. Then the VEV V renormalized with square root V, square root because it appears quadratically in the action. Then as a result, lambda lambda appears, how does it appear? So I have lambda h v plus h squared, v plus h to the fourth, actually. So so I have, for instance, then lambda h to the fourth. So h renormalizes with square root zh, and then this renormalizes with 1 over square root zh to the fourth power. That is zh to minus 2. And then on top of it, I have an extra z lambda. And again, I have the renormalization, the change in dimension of lambda, which means I compensate by adding dimensional transmutation scale mu to the power of 4 minus d. Then the renormalization of alpha and psi. This is also fixed, but let's understand why. So first of all, I've already seen here that the renormalization of the sources was completely fixed. Now let's understand, as I said, the renormalization of alpha and psi. Well, let's look at the gauge fixing term. So the gauge fixing term, there's a component here, the usual component, which is minus 1 over 2 alpha d mu a mu a squared. Okay, so we know then that this thing should not renormalize from the unbroken theory, which means that renormalization of alpha is equal to the renormalization of a squared. So alpha renormalizes with z3, with square root z3 squared. So alpha is z3 alpha renormalized, or if you want, writing generally, alpha is z alpha alpha renormalized, then z alpha is z3. But then compare with the cross term. So the cross term, I have d mu a mu psi gv ka over alpha, and then some constants. Well, no other constants. Yeah. And so this should renormalize in the same way as d mu a mu squared over 2 alpha. So in other words, d mu a mu should renormalize as psi gv ka. Okay. So so d mu mu renormalized with square root z3, and psi gz chi, then that means normalization of psi is with square root z3, and then with 1 over square root v square root square root zv square root z chi, and 1 over zg, which is the normalization of g. Okay. So then we note that the factor for the normalization for alpha and for psi is different. So z alpha is different than z psi, which is why we have put alpha and psi independent. But then the renormalization the renormalized alpha and psi are numerically the same as the ones in the Lagrangian and in the classical Lagrangian. And then in the classical Lagrangian, remember that alpha was equal to psi. So that means that alpha renormalized must be equal to psi renormalized, whereas alpha and psi are different and their renormalization is different. This is such that the renormalized values are equal, and then they could be put to 1 if you want in the Feynman-like gauge. Then another thing, we can do a one-loop calculation, and to show that the renormalization of V is different than the renormalization of H. ZV is different than ZH. Even though in the Lagrangian, in the classical Lagrangian, I have them appearing in the combination V plus H, so at the same level. So at the quantum theory, because of the gauge fixing term that treats them differently, they appear in the one loop level. They appear with different renormalizations. That's to be expected. But then, as we said, the counterpart of that is that there should be a word identity acting on the effective action. So this was all preliminaries. I will not do the exact calculation. I even did not do the exact analysis in the case of the unbroken theory, and the broken theory is even more complicated. This was done by Toft and Veltman, and they proved renormalizability at all orders, and the proof is, again, as in the gauge fixing, unbroken gauge case, it's by induction. So one only need to prove the induction step, but we didn't prove it in the unbroken case, so I didn't prove it here either. But then also, I will not do this explicitly, but even though in the unbroken case we did this explicitly, but here we will find 9 possible divergent structures. But on the other hand, we have 8 renormalization parameters: Z3, Z ghost, ZH, Z chi, ZG, ZV, Z lambda, and delta B beta renormalized, or Z mu if you want. Now, this would seem like a contradiction, but the reason is that there are 8 parameter renormalization parameters and 9 divergent structures, is that there is an extra word identity for V plus H that connects the divergent structures. So the word identity is as follows. So at tree level, the gamma hat renormalized is the action, renormalized action. And so so the action would be, so the word identity on this gamma hat, which turns into S matter, would be ddh minus ddv on S matter is equal to 0, since this S matter depends on v plus h. And then I can multiply by v. So I write it as v ddh minus v ddv. S matter is equal to 0. But then in terms of gamma 0 renormalized, I also have, so besides S matter, I also have the gauge fixing term. And then in the gauge fixing term, we have this combination psi v, right? So where was it? Psi, yeah. So in the gauge fixing term, psi. So remember, I wrote a different psi in here and alpha in here, but then in the gauge fixing term, I have psi times v. So so the dependence on v now appears together multiplicatively together with the dependence on psi. So that means I have dd, so in here I have dd psi dd psi minus vv dv of this is 0. So the logarithmic derivatives with respect to psi and with respect to v are equal. And that means that when I act on the full action, renormalized action, which is gamma 0 renormalized hat, I have psi renormalized dd psi renormalized minus v renormalized dd v renormalized, and then but then I have also this term, so plus v renormalized ddh renormalized. So this this is a word identity that reduces the possible divergences from 9 to 8, which is equal to number of renormalization parameters, which means we have renormalization. So at least at the one loop level. So that, yeah, this in principle proves the initial step, and then we'll have the induction step that I have not proved even in the unbroken case, and together this in principle proves the all order renormalizability of the broken gauge theory. And finally, another useful consistency condition, that this is not something that reduces divergences, but is just something that a consistency condition that makes sure that we did the right calculation, comes from ghost number conservation. So ghost number is defined as, if you want, so I have b times the variation of the gauge fixing function with respect to the parameter times c, right? In the gauge, in the ghost term. And so that means that I can assign a ghost symmetry to this action for the matter plus ghost, in which the ghost of B is minus the ghost number of B is minus the ghost number of C. So then as a consistency condition on gamma 0 renormalized hat, I say so B BDB minus C DDC on this is equal to 0, logarithmic derivative, in the sense again that they appear always in the product B times C. Okay, but then when I extend this by adding sources, then I have each source has now a ghost number. I don't remember if I talked about it before, but let's see. Okay, so this is the extra term in the Lagrangian, right? So the QB on A is proportional to C. So this has the ghost number of C, right? And then K there correspondingly has the ghost number of B. So I have to add K DDK since I had plus B DDB. I have to add K DDK, K mu A DD K mu A. Then the same thing for K. So K multiplies the variation of the QB of H, which is proportional to C. So K is like B. So I also have to add plus K DDK, and then variation of Ka, which is again proportional to C. So then Ka is like B. So I also have to add plus B plus Ka DDKA. And then finally, LA multiplies QB on C. But QB on C has two C's, so it's CBCC. Okay, so in order to cancel the ghost number of C, I have to add something like 2 B's, right? 2 B's would compensate for the ghost number. So since the ghost number of B cancels the ghost number of C, 2 B's would cancel the ghost number of the 2 C's. So LA is like 2 B's. So in the logarithmic derivative, I add 2 LA DD LA. Okay. So this is the consistency condition on gamma renormalized hat 0 coming from ghost number. All right, so this is everything I wanted to tell you today. Do you have any questions? Can somebody check that they can still hear me? All right. So that means you have no questions. Now, as you saw, there are no exercises for this lecture and also not for the next lecture. So the next and last lecture will be tomorrow at 10. And then after that, there will be some time because I will get on vacation and so on. So you will receive the grades rather late in July. Yeah, so I hope you'll nevertheless go to tomorrow's lecture, since it's an important one about low energy QCD and pseudo-Goldstone bosons and chiral perturbation theory. So I'll see you tomorrow at 10. Okay, bye.